Welcome to Lecture 8 of the Information Theory course on IEEE platform. I am your instructor, Sachin from the EC department in the Indian Institute of Science. Today is Lecture 8. So, just a small recap of what we did in Lecture 7 and maybe 6. So, we have a family of PMFs denoted by set of f theta of x. A theta is a parameter. Uh, X is your random variable. For example, the t of x be a function of x, then theta xt of x forms a Markov chain. So given x, t of x is independent of theta, or theta and t of x are conditionally independent given x. Then we define a definition. T of x is said to be t of x is a sufficient statistic relative to the family f theta of x. If x is independent of theta given t of x for any distribution on theta, that is theta t of x forms a Markov chain. So once you know what t of x is, you can't get any more information about the distribution from uh, x. Or likewise, once you know t of x, whatever information you can get from t of x about x, you can get at most the same amount of information from theta about x. Uh, or in a, okay. Uh, in practice, you don't know the distribution theta, so you take a sample. From that, you compute some function t of x, and then whatever information you get about the distribution theta from T of x is at most equal to the information you get from theta by observing it directly. Sorry, let me say that again. So it's called a sufficient statistic because this T of x is sufficient in the sense that um, once you know T of x, whatever you information you get about theta, you can only get that much information from x also. So observing x doesn't give you any more information about theta than observing T of x. In that case, you don't need to store your x or transmit your x if all you want is information about theta. You can only store you can store just T of x or transmit just T of x, and you will get the same amount of information about theta that you would get from x. So T of x is a something that is sufficient to know everything about theta. You don't need x anymore. You can discard x. Then if T of x is a sufficient statistic, I of theta T of x is equal to I of theta x. So whatever information about theta you can get from x, you will get that from T of x also. Generally, I of theta T of x is less than or equal to I of theta x by the data processing inequality. So that's the okay. So that's the difference between just any statistic T of x and a sufficient statistic T of x. So just a random statistic T of x, which depends on x, will give you at most the same amount of information as x. That is, processing x into T of x does not give you more information. It can give you the same amount of information or lesser information. We say it is a sufficient statistic if it gives you the same amount of information as x. Only in that case you can discard x and keep only your T of x. Suppose T of x gave you less information than x, then by discarding x and keeping only T of x, you would be losing some amount of information. So if there is any confusion, just replay the statement I said just before. Um, Maybe I made a small mistake earlier, but whatever definition I told you right now, that's the correct definition, correct meaning of sufficient statistic. Then we also saw Fano's inequality for any estimator x hat such that x, y, x hat form a Markov chain with p by definition probability that x not equal to x hat. We have a bound on h of x given x hat. So the upper bound is h of p plus p log cardinality of script x Let me write it in the next line. Is greater than or equal to h of x given script x greater than or equal to h of x given y, which can be weakened to h of p is some quantity that is less than or equal to 1. So h of x given x hat is less than or equal to 1 plus p log of mod x. So p is greater than or equal to h of x given y minus 1 divided by log mod script x. Let x and x hat be IID distributed as p of x with entropy h. The probability that x is equal to x hat is summation p square of x over all x script x greater than or equal to 2 power minus h. This follows from Jensen's inequality. With equality if and only if x has a uniform distribution. That's it for the recap. Today we'll see the asymptotic equipartition property. Before that, I'll give a few definitions that we need to define the asymptotic AEP. So these definitions are on the convergence of random variables, which you learn in a probability for random process course. We say that a sequence of random variables x1, x2, etc. converges to a random variable x. So there are three definitions. We say it converges in probability if for all epsilon greater than 0, probability that xn minus x is greater than 0 approaches 0. Second, in mean square, if the expected value of xn minus x whole square approaches 0. So these are all as n approaches infinity. And finally, we say it converges with probability 1 or almost sure convergence if the probability that limit of xn as n approaches infinity is equal to x is equal to 1. So it's best if you go back, find a probability textbook and check if these are right. A mean square is right, but in probability and almost sure convergence, you have to check if I haven't made a mistake. Alright, I went back and checked and the definitions are correct. What these definitions mean are that uh, in mean square error, it's easy to understand. The value of xn minus x whole square, the expected value of xn minus x whole square approaches 0. So if it's a discrete random variable, then you weight xn minus x for each outcome with the probability of that outcome. So it's the weighted sum of magnitude of xn minus x whole square. For example, if there are six outcomes, let's say they're throwing a dice, so there are six outcomes, and to each of the outcomes you assign a value. So if it's even, you give it a value 1, and if it's odd, you give it a value minus 1. So this is your x. Then x1, suppose it's minus 2, 2, minus 2, 2, minus 2, 2. x2 is minus 1.5, 1.5, minus 1.5, 1.5, minus 1.5, 1.5. x3 is minus 1.1, 1.1, minus 1.1, so on. So as you go, as n goes larger and larger, your value, the value of xn. So now, yeah, if you're looking at mean square error, what you have to do is you have to find the mean value. Mean value is 0, and the difference expected value of x1 minus x whole square. Suppose they are equally likely outcomes, then expected value is summation p of wi for all outcomes wi, magnitude of xi of x1 of wi minus x of wi whole squared. And since I'm assuming all outcomes are equally likely, then p of wi is 1 over 6 for all outcomes, so it would be 1 over 6 summation modulus of x1 of omega I minus modulus of x1 of omega I minus x of omega I whole square. For the outcome 1, the difference is minus 2 minus minus 1, which is minus 1. Magnitude is 1, 1 squared. So it's 1 squared plus 1 squared for 6 outcomes. So it's 6 over 6, 1. So that's the expected value. of the mean squared error. Expected value for x2 minus x whole square, this would be 1 over 6, and the summation is minus 1.5 minus minus 1 is minus 0.5, whole square is 0.25. The 0.25, you have 6 terms, so it's 0.25. So E of x3 minus x whole square is again 1 over 6, minus 1.1 minus minus 1 is minus 0.1, whole square is 0.01. There are 6 terms like that. So it is 0.01. So as n goes higher and higher, the value of this expected value is going lower and lower, and it is approaching 0. So that's the mean squared error, convergence in mean squared sense. Convergence in probability is kind of similar, where for each outcome, the difference in the absolute value of the difference in xn minus x is greater than epsilon must go to 0. So we should be able to get it arbitrarily low by picking n sufficiently large. So for x1, the difference x1 minus x is minus 1, and suppose I pick epsilon equals half, this is not really a good example to show convergence in probability. Anyway, suppose someone gives you epsilon is equal to half, then so they give you epsilon is equal to half and they say delta is zero point 0.1, then you should be able to find some value of n such that probability of x n minus x greater than epsilon is less than delta for all n greater than capital N. This should be You should be able to do it for all values of epsilon and delta which are positive. So for epsilon is equal to half and delta is equal to 0.1, you have to find capital N such that probability of xn minus x is greater than half is less than zero point 0.1 for all n greater than capital N. Now if You choose for n is equal to 1, you have probability of xn minus x greater than half. This will be true for all outcomes. Okay. Here, I've given probabilities such that this modulus of xn minus x is the same for every outcome for each random variable. But uh, in other problems, for each outcome, they might have different values, and you will have to make sure that this statement is true for all outcomes omega. These are the outcomes omega. 43, 4, 5, 6. Now, probability that modulus of x1 minus x is greater than half is, what is it? So x1 minus x is always modulus of x1 minus x is always 1, which is greater than half. So it's 1. Then probability that x2 minus x is greater than half is uh, x2 minus x is zero point 0.5 for all outcomes, so it's greater than half for all outcomes, so its probability is 1. And probability that x3 minus x is greater than half is x3 minus x is zero point 0.1 for all outcomes, so it is less than half for all outcomes, so the probability that it is greater than half is 0. So for these values of epsilon and delta, capital N is equal to, actually it is let's just change these to 1.6 to avoid confusion. So now N is equal to 3. And for all N greater than capital N, probability of xn minus x is greater than epsilon is less than delta. Right. So what happens is, uh, okay. Now here I took all these outcomes are equally likely, but suppose each of these outcomes had different probabilities. Because this is half, this is 1/4, this is these were 1/8 or 1/16 each, does something like that. And these values are also different. This is -2, this is -2.5, this is 2.5, this is 2.1, something like that. Then, so in this case, if you want to check if there is probability in uh, if x1, x2, etc. up to xn converge to xn probability, then what you have to do is someone will give you an epsilon value and a delta value. Then you have to find the set of all outcomes such that x of xn of omega minus x of omega is greater than epsilon. Then probability that xn minus x is greater than epsilon is equal to probability of the set of all outcomes such that xn of omega minus x of omega is greater than epsilon. And this will have some probability, which is because it's a subset of the sample space. So this probability must be less than delta for all n greater than capital N. There must be some capital N such that somewhere here, such that for all the random variables below that, the probability of this set of outcomes for which xn of omega minus x of omega is greater than epsilon is less than delta. So earlier I think I said it should be true for all outcomes, so that's not exactly it. So for the set of outcomes for which x of xn minus x is greater than epsilon, the probability of that set should be uh, less than delta, where delta can be chosen arbitrarily. So you should be able to do this for any values of epsilon delta. Similar to the epsilon delta definition of limit of a function. Finally, when you say x1, x2, xn converge to x with probability 1 or almost surely, then what it means is that you have a set of outcomes. You have mapping x, a random variable, which maps the outcomes to the real numbers. And then you have a sequence of such mappings. Now, so there will be a set of outcomes for each of these x1, x2, x3, xn, etc. There will be a set of outcomes for which xn is not equal to x, and as you increase n, the probability of this set of outcomes should be equal to 0. So the probability, so that means as n approaches infinity, whichever outcomes occur with non-zero probability, for those outcomes, xn and x should match. Xn should be equal to x. And if there are outcomes which uh, occur with probability 0, then in those at those outcomes, xn and x need not match. So it is enough that as n approaches infinity, xn and x match exactly at all the outcomes which occur with non-zero probability. So in that case, we say that xn converges to x almost surely. It's not that xn takes the same value of as x everywhere. It's that wherever xn doesn't take the same value as x, that particular event won't occur at all. So it's like saying when you toss a coin, you'll you'll get a heads or tails, or it might, in the rare event, um it might stand right in the middle. It might not fall down to heads or tails. So it might stand up straight. So we are saying that, but in general, we uh, assume that whenever we are modeling a coin toss, we assume that we only get heads or tails. So if you include the middle state where it's standing up straight as one of the outcomes, then the probability of that outcome is 0. That's what we usually assume. So you can either take the coin toss as an event of three outcomes, heads or tails. Heads occurs with some probability p, tails occurs with probability 1 minus p. You could also say h or tails or middle, where it stands up straight. And heads occurs with probability p, tails occurs with probability 1 minus p. This middle outcome occurs with probability 0. You could model your coin toss in that way also. So in such a case, the difference is, suppose you don't know the possible outcomes of you don't know the probability of these events. Suppose there is a scenario in which um, your coin could be in the middle instead of heads or tails. Then when you're doing an estimation, if you don't anticipate that it could be in the middle, if you think that only heads or tails can occur, and you have an estimator that estimates the probability of getting heads or tails, then that will give you a different kind of estimate than taking the outcomes to be HTN and then finding out the distribution of HTN. So if you take HNT as the only possible outcomes, then M, there's no M in this. So when you perform an experiment and if the coin actually lands up in the middle, then you will be in trouble. So in such a scenario, what we are saying is, since m occurs with zero probability, for x1, x2, etc., maybe the value of x1 is x is x takes the value 1 for heads and 0 for tails, but x1 takes the value 1.1 and 0.1, x2 takes the value 1.2, 1.01, 0.01, and x for the outcome m, x takes the value 0. Say x1 takes the value 2, this takes the value 3. But as n uh, becomes larger and larger, we want xn to be equal to x, it should go to 1. And for tails, it would go to 0 because they occur with non-zero probability. But for m, xn can be 4, doesn't matter. So xn and x don't match at this outcome, but this outcome has a probability 0. So we are not worried about that. That is a crude explanation of convergence. I apologize if I have made any mistakes or if I have confused you. It's better to go back and refer to a textbook for the precise definition and examples. But this is enough for the purposes of our course. Now, with that, we can proceed with the content. Theorem 3.1.1, asymptotic equipartition property. If x1, x2, etc. are IID distributed according to the distribution P of x, then minus 1 over n log of P of x1, x2, xn, etc. approaches h of x in probability. The proof is simple. We have functions of independent random variables are also independent random variables. So xi is our IID. P of xi is also actually a random variable, which is since it's a function of uh, xi. And p of xi is a function of xi. Log of p of xi is also a function of xi. Since xi is our IID, log of p of xi is also IID. Hence, by the weak law of large numbers, we can write minus 1 over n log of p of x1 to xn is minus 1 over n summation log of p of xi I is equal to 1 to n. So log of p of x1 to xn is log of P of x1 into P of x2 into etc. up to P of xn because they're independent. And then log of products is a sum of logs. So it becomes summation I is equal to 1 to n log of P of xi. And by the weak law of large numbers, so this is the sample mean of log of P of xi, which converts us to the expected value of the uh, variable, which is in this case log of P of x in probability, that is by weak law of large numbers. But minus expected value of log P of x is the entropy h of x. So that's the proof. So minus 1 over n log of P of x1 to xn is the sample entropy. H of x is the true entropy of the distribution. What exactly is going on is you conduct n independent trials of the same experiment, then you note down the value of, uh, sorry, you you have an experiment and you have n independent uh, random variables. You do the experiment. There are two ways to understand this. This is the first way. You do the experiment and then you have n different values uh, for n different random variables, right? Each of the random variables takes on a value based on the outcome of the experiment. Then you uh, that for this set of n outcomes is one particular sequence of all possible sequences of outcomes that you could get, of all possible random variable values you could get. So that has a particular probability of occurring. You find the probability of that particular set of random variable values occurring and take the log of that and divide it by n. So this is the sample entropy. So if you don't know the average value of some random variable, say, right? Then what you could do is you repeat the experiment n times, do independent trials, and note down the value of the random variable in each trial. So in each trial, you give it a different name, x1, x2, xn. Xi is the ith trial. The xi is the value of random variable value in the ith trial. Then you sum all xi's and divide it by n. So that gives you a kind of average, but it is not the exact average based on the distribution because every time you do this set of any independent trials, you might get a different sequence and you might get a different average value. Only guarantees that we can give is that if you do a large enough number of trials, then the average you get by doing these any independent trials and taking the sample mean will get closer and closer to the true average value of the distribution. Similarly, here, if you don't know the distribution of the random variable x, or you don't know the entropy exact distribution or the exact entropy of the random variable x, then you perform a series of experiments, find out the uh, sequence of random variable values that you get, find the probability of that sequence occurring, and take the negative log of that and divide it by 1 over n, divided by n. And that will be close to the true entropy of the distribution h of x. So what is hiding in this um, proof is the following. So suppose you are conducting an experiment and the experiment has some sample space omega and you have random variables which take values from this set script x, uh, and there are a1, a2, a cardinality of script x. These are the values in script x. Then you perform n trials, independent trials. Each trial you get a value. You note that down. So suppose here you get a1, here you get a2, then again you get a1, then you get a2 somewhere here, and so on. Suppose the value a1 occurs n of a1 times, a2 occurs n of a2 times, etc. A script x occurs n of a script x mod script x times. Then minus 1 over n log of p of any particular sequence x1, x2, etc. xn is minus 1 over n log p of x1, p of x2, etc. p of xn. So in x1, x2, xn, so this a1 occurred n of a1 times in these among these x1, x2, xn. Each of these xi's can be any one value from uh, script x. So suppose ai has occurred n of ai times in this sequence, then you'll get p of ai n of ai times, so it's p of ai power n of ai times p of a1 to the power n of a1 into p of a2 to the power n of a2, etc. to p of a mod script x power n of a mod script x, which is nothing but summation, negative summation n of ai divided by n, I is equal to 1 to mod script x log of p of ai, because log of a product is the sum of the logs, and log of something to the power something else is that something else times log of. So log of p of a1 power n of a1 is n of a1 times log of p of a1. That's all. Now from weak law of large numbers, n of ai divided by n converges to p of ai as n approaches infinity. That is, if you take a large number of experiments, the fraction of times that AI occurs is P of AI. So if you are tossing a coin, then if the probability of the heads is half and the probability of tails is half, then if you do 1,000 coin tosses, then 500 of them will be about 500 of them will be heads and 500 will be tails. So the fraction of heads is 500 out of 1,000, which is half, which is equal to the probability of heads. Suppose probability of heads was one fourth and probability of tails was three fourths, then uh, heads would have occurred 250 times out of 1,000 trials. So the fraction 250 by 1,000 is one fourth, which is equal to the probability P of AI. So as you do more and more experiments, this experimental value of the fraction of uh, the outcome AI, which is given by n of AI by n, approaches the true value, approaches the probability value of the particular outcome AI. So now, therefore, minus 1 over n log of p of x1 to xn approaches minus summation p of ai log p of ai is equal to 1 to strip mod x. What is this quantity? This is nothing but h of x. So that is the proof when the textbook glossed over that point, but they assume that you understood what exactly they are doing, which is they're using the notation minus e of log p capital X. So in that notation, it's easier to write, but this is what is hiding beneath the notation. Now, once we know this, we move to the topic of typical sets. So yeah, here we saw that from the weak law of large numbers, the number of times an outcome occurs, the fraction of times an outcome occurs is close to the probability of that particular outcome. So in say 1,000 outcomes, we saw that um, if the probability of heads is one fourth, then 250 you would you would probably get around 250 heads and uh, 750 tails. But that is an intuitive concept. Now I'll show you something that's a little subtle. So suppose you toss a coin, let x be a random variable. That takes on the value 1 if the outcome is heads, and 0 if the outcome is tails. Suppose you toss the coin 10 times and xi is the random variable that the random variable associated with the ith trial. That is xi of omega is equal to x of omega in trial in the ith trial. So you can take x1, x2 up to xn as 10 different random variables where x1 of omega is 1 if the outcome of the first trial is heads, and 0 if the outcome of the first trial is tails. Suppose you have a biased coin with probability that heads occurs is equal to P, which is 3 over 4. The probability that the tail occurs is 1 minus P, which is 1 over 4. Or let's say this is 3 over 5, and this is 2 over uh, 2 over 5. Then consider three possible sequences. First sequence is sequence of all zeros. Second sequence is a sequence that contains four zeros and six ones. Third sequence is a sequence of all ones. So, which do you think is more likely to occur? Now, you would think that if someone asked you this question, you would think so 3/5 of the time you would get a head, and 2/5 of the times you would get a tail. Since there are 10 outcomes, out of them, 6 heads and 4 tails is what you would expect. your outcome to look like. So you might say, you might think 0, 0, 1, 1, 0, 0, 1, 1, 1 is the most likely among the three. But the probability of the sequence of zeros is 2 by 5 power 10. Probability of 0, 0, 1, 1, 0, 0, 1, 1, 1 is probability uh, of tails occurring 2 by 5 4 to the power 4 into 3 by 5 power 6, which is 1 over 5 power 10 into 2 power 4 into 3 power 6. This is 1 over 5 power 10 into 2 power 10, which is 1 over 5 power 10 into 2 power 10 is 1024. This is 1 over 5 power 10 into 2 power 4 is 16. 16 into 3 power 6. That's 729. 16 into 729 is 11,664. Probability of the outcome 11111 is 3 by 5 power 10, which is 1 over 5 power 10 into 3 power 10, which is 1 over 5 power 10 into 59,049. So he can, by calculating the actual probability, we see that probability of the sequence 11111 is much higher than the probability of the sequence 001100, etc., which is much higher than the probability of the sequence 0000. So probability of 11111 is greater than probability of 0011001111. Therefore, but intuitively we feel 0011001111 intuitively a sequence of the type is more likely to occur than 11111. So our intuition is correct in this case because there is only one sequence of all ones, which is 1 1 1 1 1, but a large number of sequences with a large number of sequences, exactly 7 choose 10 choose 4, which have 4 zeros and 6 ones, and each of them is equally likely. So, even though each of the particular sequences with 4 zeros and 6 ones is less likely than the particular sequence 1 1 1, together all sequences with 4 ones and 4 zeros and 6 ones, if you consider that to be an event, that is the event that your sequence has 4 zeros and 6 ones, then that event is a much higher probability event than the event of getting all ones. So even though you might not see this particular sequence 0011001111, you're more likely to end up with a sequence that has 4 zeros and 6 ones. Where those 4 zeros occur and 6 ones occur, that that is not uh, we can't really guarantee, but we can guarantee that a sequence with 4 zeros and 6 ones in some place among the 10 places is much more likely to occur than a sequence of all ones, because there is only one way in which a sequence of all ones can occur, but there are a large number of ways in which a sequence of 4 zeros and 6 ones can occur. There are also a large number of ways in which a sequence of 3 zeros and 7 ones can occur. And there are also a large number of ways in which a sequence of 5 zeros and 5 ones can occur. But so to make this more precise, we define the concept of a typical set. So again, we have a definition. The typical set A epsilon of n with respect to some distribution p of x. So the typical set will change if the distribution changes. Is the set of, this is important, the set of sequences, n-length sequences x1, x2, xn belonging to split x n. So each of these x1, x2, xn is a one particular realization. So if you're taking coin tosses, then each of these x1, x2, xn is one of these types of sequence 1 1 0 0, a sequence of ones and zeros, with the property, the probability of the sequence is somewhere between 2 power minus n h of x minus epsilon and 2 power minus n h of x plus epsilon. So this is a bigger number, n into h of x plus epsilon. So 2 power minus a bigger number is 1 over 2 power a larger number. So if you write this as 1 over 2 power n into h of x plus epsilon, it will be more convenient to remember. 1 over 2 power n of h of x minus epsilon. So n of h of x plus epsilon is larger. So 2 power that quantity is also larger. So the reciprocal is a smaller number when compared to 1 over 2 power n of h of x minus epsilon, where you are subtracting epsilon from h of x here. So this quantity is smaller than this quantity. Therefore, this entire thing denominator is smaller than this denominator. Therefore, the reciprocal, this entire thing is larger than this is the reciprocal. So h of x minus epsilon shows up in the upper bound and h of x plus epsilon shows up in the lower bound. So we define a typical set in this way. That is, it is the set of all sequences which have a probability within these two bounds. So if you define it this way, then we have a theorem which says if a sequence x1, x2 up to xn is a typical sequence, that is, it belongs to the typical set, then the sample mean minus 1 over n log p of x1 to xn lies between h of x plus epsilon and h of x minus epsilon. Second point, the probability of this typical set a epsilon n is greater than or equal to 1 minus epsilon for n sufficiently large. So if you conduct enough number of trials, then the probability of this typical set is very high. So you can make it as high as you want. Of course, it will always be less than 1, but you can make it as close to 1 as you want, in the sense that the probability that a sequence from this set occurs is close to 1. The third point is the number of elements in this typical set is upper bounded by 2 power n h of x plus epsilon, and the number of sequences in this set is lower bounded by 1 minus epsilon times 2 power n h of x minus epsilon. The proof of this is as follows. One follows from definition. That is, by definition, p of x1 to xn is greater or equal to p of x1 to xn is between 2 power minus n h of x plus epsilon and 2 power minus n h of x minus epsilon. To take log to the base 2, log of p of x1 to xn is between minus n h of x plus epsilon greater than or equal to n h of x minus epsilon. You divide by minus n. When you divide by a negative number, the inequality uh, changes direction. So log of p of x1 to xn divided by minus n, or minus log p of x1 to xn by n, is greater or equal to this right side quantity divided by minus n, which is h of x plus epsilon, but less than or equal to actually this was h plus epsilon, this was h minus epsilon. Like I explained earlier, this is actually reciprocal of 1 over 2 power n h of x minus epsilon, and since h of x minus epsilon is smaller, the reciprocal of its power is larger and it forms the upper bound. So now when you switch, you get h of x minus epsilon and h of x plus epsilon. Proof of the second point, probability of this set is greater than or equal to 1 minus epsilon. Proof follows from the AP theorem, since it implies probability of set of all sequences belonging to A epsilon of n approaches 1 as n approaches infinity. That is, for any delta greater than 0, there exists n0 such that for all n greater than or equal to n0, probability of minus 1 over n log of p of x1 to xn minus h of x is less than epsilon is greater than 1 minus delta. So the another way of writing the asymptotic equipartition property. So the asymptotic equipartition property says that if x1, x2, etc. are IID distributed according to distribution P of x, then minus 1 over n log of P of x1 to xn approaches h of x, right? In probability. When you mean when we say in probability, then from the convergence in probability, we have for all epsilon greater than 0, probability of xn minus x greater than epsilon approaches 0. That is, for any epsilon and delta, there exists an n0 such that all n greater than or equal to n0, probability of xn minus x greater than epsilon is less than delta. If you switch it up and write probability of xn minus epsilon is less than epsilon, then that will be greater than 1 minus delta because it's the complement um, event. So here instead of xn, we have minus 1 over n log of p of x1 to xn, and it is converging to h of x instead of x. So probability of minus 1 over n log of p of x1 to xn minus h of x, the magnitude of that is less than epsilon, is greater than 1 minus delta for uh, sufficiently large, and we can choose epsilon and delta as however we want. A probability which setting delta is equal to epsilon, probability of minus mod minus log of p of x1 to xn minus h of x is less than epsilon, is greater than 1 minus epsilon. But by definition, we have for a typical sequence, or rather by part 1, which follows from the definition, uh, set of all outcomes such that the typical set of all outcomes such that p of x1 xn um, or rather um, from part 1 minus log p of x1 to xn is greater than or equal to h of x minus epsilon less than or equal to h of x plus epsilon. So if you subtract h of x from both sides, you are left with minus log p of x1 to xn by n minus h of x is between minus epsilon and epsilon. You could write that as minus log of p of x1 to xn by n minus h of x. The model of that is less than epsilon, less than or equal to epsilon. So a epsilon of n is the set of all sequences such that set of all sequences x1 to xn such that minus 1 over n log of p of x1 to xn minus h of x is less than epsilon. So that's actually the typical set. Therefore, P probability of the set A epsilon of m is greater than or equal to 1 minus epsilon in probability. Is equal to 1 in probability or approaches 1 in probability or is equal to is greater than or equal to 1 minus epsilon for sufficiently large n. Finally, uh, we have bounds on the two bounds on the size of the set. We have one is the summation of the probability for all sequences such that the sequences belong to script x power n, which is greater or equal to sum of all probability of all sequences such that the sequence belongs to a typical set. Because a typical set might not contain all the sequences. There might be non-typical sequences with non-zero probabilities, but dropping a few of the terms will only decrease the probability. It won't increase the probability because probabilities of all the sequences are positive or non-negative. But from the lower bound on the probability of a typical sequence, we have p of x is greater or equal to 2 power minus n of h of x plus epsilon. This is true for all sequences in the typical set. And this 2 power minus n of h of x plus epsilon is independent of the uh, sequence x itself. It is the same for all x in um, a epsilon n. So this is 2 power minus n h of x plus epsilon times cardinality of a epsilon. Okay. And bringing it to the other side, a epsilon of n, the cardinality is less than or equal to 2 power plus n h of x plus epsilon. To get a lower bound for this, we have for sufficiently large n probability of a epsilon of n greater than 1 minus epsilon. So p of summation of p of x in the typical sequence, probability of a epsilon of n is equal to this, which is greater than 1 minus epsilon. But each of these probabilities itself is less than or equal to 2 power minus n of h of x minus epsilon. So 2 power minus n of, and this 2 power minus n h of x minus epsilon is independent of x bar and the sequence itself. As long as it belongs to a typical set, it has the same bound. So you get cardinality of a epsilon of n greater or equal to 1 minus epsilon, from which you get a epsilon of n greater or equal to 1 minus epsilon times 2 power n h of x minus epsilon. So that's it for this lecture. So in this lecture, we gave a small recap after a long time. I'm taking lecture, so I gave a small recap of the previous what I did in the previous classes, and I had a small discussion on convergence of random variables in different senses. Uh, then I gave you the statement of the asymptotic equipartition property and its proof. I explained the proof in more detail. So, and then I motivated, I gave a motivating example for why we study typical sets. So it's a motivating example for studying typical sets. And then I gave you the definition of a typical set. Then I gave you properties of a typical set. So what these properties mean physically is that a typical set is is a set such that uh, it contains all the sequences that are typical that would occur typically if you did the experiment n number of times. So if you take a sequence in the typical set, then its sample entropy will be within a small epsilon difference of the true entropy h of x. The probability of the typical set is almost equal to 1, so it's greater than or equal to 1 minus epsilon, which means that it is a high probability set. Uh, and also, we gave bounds on the size of the typical set. So it's upper bounded by 2 power n h of x plus epsilon and lower bounded by 1 minus 2 power n h of x plus x minus epsilon. So the cardinality is between these two bounds, so it is approximately, you could say it is approximately equal to 2 power n h of x. So there are approximately 2 power n h of x sequences. Each of the sequence is approximately equally likely, so it's approximately a uniform distribution on the sequences in the typical set. And uh, the sample entropy of each of those is equal to the true entropy of the distribution. Okay, so I'll repeat that again. Uh, okay, there are three main points, three statements that you can say about typical sets. So typical set is a high probability set that contains most of the sequences that are likely to occur. So it's a set with a probability close to 1. Each of the sequences in that particular set is equally likely to occur. So the sequences in a typical set have approximately a uniform distribution, and the number of sequences in the typical set is approximately equal to 2 power n h of x. So since all of these are equally like almost equally likely, each of the sequences has probability approximately 1 over 2 power n h of x or 2 power minus n h of x. Those are the three main things, three main statements that you need to know about typical sets. In the next class, we'll continue with data compression. Thank you.